Okay. Hello everyone. I hope I'm audible loud and clear. Okay, great. So let's start.
Yeah, start.
What did we do in the last session? Yes, who will tell me? We did. Sure. What did we do in the last session? Central limit theorem, right? Is it better, Vaibhav? Saurav, not. You can go through the project, but some of the projects will require. No, in fact, you can go through the project, but it will require you to run models, right? Which we have not done, right? So you'll have 2 weeks after the completion of session. Also, you'll have 2 weeks. So go through it. Okay. Yesterday we did ggplot2. Then we started with inferential statistics and central limit theorem. Who will tell me the crux of central limit theorem? Though it's there on the screen, but I wanted to tell me the crux. What does central limit theorem states? No one? What does central limit theorem states? Okay, let me just distribution of the sample means will be equal to the normal distribution. Sampling distribution of the sample means will be equal to the normal distribution, right? Approximates the normal distribution, right? We not say will be a normal distribution. It approximates a normal distribution. Okay. Then three more results were there in the one in red, blue, and orange. Right. I'm quickly reading through it. Though explanation was done yesterday, and we anyone tried simulation? It's a wonderful tool. You should try simulation. You'll get a better idea of what central limit theorem is and how you can just try different mm, samples. You can try different ob- number numbers in the sample, right? Picking the different number of observations in the sample, right? And see how the results vary. Okay. So quickly, in short, average of all sample means will be equal to the population mean, right? Average of the all sample means, right? So if we take all the sample means, all the samples from the population, how many is are possible? Yesterday we saw 100,000, 200,000, right? And we calculate the mean of those sample means, right? We calculate the average of those sample means, it's going to be equal to the population mean, right? Then distribution of the sample means calculated by repeating samples will tend to normality as the size of the sample gets larger. Means we saw this also yesterday. We took five sample size, then we took I think 10 sample size, and it the 10 was tending to normality more. I mean prior to 5, right? It was like 10 will be faster moving to normality, right? Okay. And last, standard deviation. This standard deviation of the sampling distribution decreases as the samples that were used to calculate the means for the sampling distribution increases, right? See, just think, if the samples, if the size of the sample means that if I take a bigger size, right? Let's say I take a size of 5, sample size of 5, right? And this is my population, which you can see, right? I'll quickly show this in the simulation. I create a very skewed distribution. Now, far away from, this is far away from normal, right? No relation with normal, correct? This is my population, right? I take a 5. Right now, n is equal to 5. I So can you see this somewhere? This is my population mean, right? So this is near the population mean, right? But if I take another one, it can land up again. See, this was by chance, it just landed there. Let me take another. See, it's different. And sometimes you'll find it comes to be far away because the sample size is only 5. It can really skew my mean. It can put my mean, sample mean, far away from the actual mean, right? But if I take n equal to, let's say, 25, right? I'm just taking bigger n, right? Now see, 25 are actually almost half of them are, notice, isn't it, isn't it closer to the, isn't it closer to the actual mean compared to 5? Yes. Why is it happening? Because, okay, why is it happening? Because more are the observations, right? More are the observations in the sample. There, there is going to be negative, mm, half of them, approximately half of them will be in the negative territory, and half of them will be the positive territory of the population mean, right? So it's going to balance out. But smaller the population or smaller the n, each n, let's take n equal to 2 and see. Oops, sorry. Let's take n equal to 2 and we'll see. See now, the n is small. This is fine. This is also fine. Okay, can you see? It's, oh, it's normal. That's why I was wondering. Wait, I have to change the population. Let's change the population to a skewed one. Okay, now see, n equal to 2. See how far it is from the population mean. Can you see? Are you getting this? If I take n20 and do this animation, it will be closer to the, so that's why standard deviation of the mean of the population mean, right? Mean of the sample mean is lesser when n increases. Is that clear? This point is clear to all of you? Can we proceed? Right? So quickly we'll proceed to hypothesis now. Now, you know, all of you know the ground or the ground of hypothesis of inferential statistics, right? Right? What is the base of inferential statistics? It is because of this central limit theorem, we are able to take samples and infer the characteristics of a population, right? The mean of the population, right? So now coming to hypothesis. What is the meaning of hypothesis? Can anyone tell? Forget about the statistical meaning, English meaning. Assumption, right? Hypothesis means an assumption that we want to test. Okay, yeah. Now when you say test, you are coming to statistics, right? But yeah, in English, hypothesis means you are just assuming something, right? And now when you want to test that, statistics come into picture, right? And tell me, I'll start with a example of hypothesis. Right? For hypothesis, I'll start with an example. Let's say a company is planning to increase its marketing expenditure, right, for the products it produces, right? It is planning to increase the marketing expenditure, and currently their profit ratio, profitability, right, is 25%, and they are expecting that after increasing the marketing expenditure, or maybe some more steps they are going to take to increase the profitability, right? They are expecting that their profitability will increase to 30%, right? Clear? What is the situation? Is it clear? Right? So can you tell me what I would want to test? Will I be will I want to test 25% profitability or 30% profitability? What will be what I would want to test? 30%? You never test the as is situation which is actually there, right? If I say today I'm okay. Uh, can I say I want to test whether today in this class 30 students will be there? No. I would want to test whether tomorrow there will be 30 students or not, depending on how the session went today. Right? Okay? Clear? So claim. It is a claim which is not a hypothesis is a claim which is to be tested, which we have to test. It is something which is still unproven, right? We have to prove it that that can happen. We have to by doing some tests. Clear? So hypothesis is a claim. Yeah, it can be true or false. Correct, right? It can go either ways, right? Hypothesis is a claim or a statement or assumption about the population parameter. So, like I said, I am assuming that making these changes, assumption, notice, right? I am assuming that making these changes, my profitability will increase from 25%, which is currently, to 30%. I am not going to test 25%. It is actually there. What's there to test, right? I will be testing the 30% thing, correct? Right? Now, hypothesis, it's a problem statement that leads you to some analysis. The problem statement that leads you to some analysis is called hypothesis, right? Problem statement here means a statement that is significantly different from the as is situation, right? Now, this word significantly different will come to this in detail. For now, if you read it in a plain English also, it says we are going to test a statement, we are going to test a claim which is significant, which is actually different from the as is situation, right? That is hypothesis. Hypothesis testing is the technique of inferential statistics where we test the claim or statement that the researcher or a statement of the researcher about the population, right? Researcher, or you can say data scientist, right? So even as a data scientist, you will be assuming some things, right? And then you will be backing it up with data, right? Okay, clear? What is hypothesis? Is it clear? Right? Some examples of hypothesis, right? Can you give me some claims in maybe business or non-business? I just want you to think on some claims that you can make, right? Let me start, right? Next year, I'm expecting the sales to go to 120,000 crores or 120 crores, 120 million, right? Currently, my sales is 100 million. I'm expecting the sales to go to 120 million, right? So that's a hypothesis. Another hypothesis. In a class, oh, okay, in a school, the principal is expecting that the average IQ of the students of his school is more than the average, right? That's again a hypothesis which needs to be tested. Okay. Yes, Vaibhav. Now I want some of you to please share some hypotheses that you think. Can EV car sales grow over engine car sales? Okay. EV car sales, the growth of EV car sales will be more than the engine car sales in next 5 years, let's say, right? Okay, right? So you have to be specific. Okay, let me go to the next slide. It will really help you, right? Maybe thinking a better or closer statement. Yeah, characteristics of hypothesis: clear, specific, and testable or researchable. It should be clear, right? Can a EV car sale grow? It's a question first of all, right? Right. So we'll say the growth rate of EV car sales is expected to be more than the engine car sales in next how many years, right? You have to be specific. Yes, Nisha. Temperature will rise 4 degree globally in next 5 years. Yes, very good. Good, right? RCB winning IPL next year. Again, it's a very vague statement. RCB will win the finals, right, in IPL next year. Okay, then there will be growth of 50% data scientist jobs in next year. Okay, good. Efficacy of vaccination against corona to increase from 30 to 40%. Excellent, Suman. In next 6 months. Okay, great. Thank you so much for sharing. Right, so you got it. What is hypothesis? Claims that is still not tested, and we need to test it. Okay, so fuel prices raise is coming in coming days. Fuel prices are expected to rise by this much percent. See, if you don't specify it, you will not be able to test it. Ultimately, we are testing it, na, with some numbers, right? If you don't pick can you test this? Fuel prices raise is coming in fuel prices raise in coming days. It's a very vague statement, right? So let's make it specific, clear, specific, and testable. Okay. Remember the first two, clear and specific. Testable, of course, we are going to test, right? Testable is that you should be able to uh, get or you should be able to collate the samples, right? For that claim, data should be available, right? Only then it is testable. Okay, right? So, okay, its hypothesis is the first step in designing and conducting the research. Clear, specific, testable. It's a link between theory and research. So theory means what you are assuming, and research, sorry, research what you are researching and then putting it into use, right? Leads to new discoveries. Okay, okay. Hypothesis must satisfy the following requirements. It's a declarative statement. It postulates relation between variables, very important. Of course, there has to be some relation, only then we will be able to test a claim, right? Okay, reflect the theory which will guide the research, be brief and concise, be testable and or provable, right? So these are the characteristics of hypothesis, right? Okay. Now there are different types of hypothesis: simple hypothesis, complex hypothesis, statistical hypothesis, null and alternate, right? So let's see what is was simple hypothesis. When the relationship is between two variables, right? One of them is called independent variable or the cause. The other one is called the dependent variable or effect, right? Example, older workers are more loyal to the company. right? So here, this is a statement, but it is not a measurable statement. Right now, I am not measuring it, right? Specific. There is nothing specific in it. So you have to maybe come up with a measure of loyalty, right? And then we will be able to test the statement, right? Yeah, exactly, Vaibhav, you're right, right? So, but yeah, this is a claim is correct. Usually, when you are working in corporates, right? When you are working in business, your your senior management or your management are going to give claims like this. They are going to give you statement like this only. Then you have to think how you can convert those statements into a quantifiable or measurable statements, right? So older workers are more loyal. Let's say in terms of loyalty, how can we measure loyalty? Let's say number of years, right? The workers that are more older workers in age, they stick to company, stick to the company, or they stay with the company for a longer period of time, right? Let's say they stay with the older workers stay with the company for at least 5 years or more. Getting it? Measure of loyalty. I'm just taking the stay of an employee as a measure of loyalty here, right? Okay. Then complex hypothesis. When relationship is a relation between two or more independent variables. Here I have two or more independent variables. Okay. Do you first, since I have started using independent, do you know what is independent and dependent variable? Anyone who has any doubt regarding it? Okay. Let me take an example. Y is equal to 20x plus 3. Let's say this is my function, right? Fx. Here, x is my dependent variable, right? Based on which y is the value of y can be calculated, right? So dependent variable is the variable. Sorry, y is. Did I say x is a dependent variable? I think I mentioned it wrongly, right? Sorry, really sorry about that. Yeah, x is a independent variable. See, value of x is not dependent on anything, but the value of y is dependent on x. Okay, right? So x is a independent variable, right? And y is a dependent variable. Y is the effect and x is a cause, right? Is this clear? Now, can you tell me, let's say the the number of accidents mm, in a city. No, no, no. Let me change the 5% of accidents in the city are caused due to mechanical issues, right? So, what is dependent and what is independent? 5% of the accident of cars is caused by mechanical issues. Mhm. First, tell me independent variable. Mechanical issues is independent variable, right? And number of accident or the percentage of accidents is dependent variable. Clear? Right? So in this, which is dependent and which is independent? Older workers are more loyal. So can you tell me which is the dependent independent? First tell me the independent variables. Independent variable. Older workers, the age of the worker, right? That is an independent variable. And dependent variable, more loyal or their stay in the, right? they stay in the company, right? Older workers are more loyal. Okay. Next, relation between two or more independent. Oh yeah, complex hypothesis: relation between two or more independent variables or two or more dependent variables. So if it is not one to one on either side, it could be like this: y equal to 20x plus 5z plus 3. So y is here dependent on two independent variables. Okay. So that is called complex hypothesis, right? Wherein two or more independent, or it could be other way around also. There could be two dependent variables also, right? Example: global warming causes icebergs to melt, which in turn causes major changes in the weather patterns. So what is my dependent variable first of all? No, that's independent, Nisha. Changes in weather patterns is dependent variable, right? Yeah, I first asked you dependent, so I think you just mentioned global warming, right? Yeah, changing weather patterns is the dependent effect, right? And global warming and icebergs, they are independent variables. Clear? Okay, can I proceed? Okay. Now, simple and complex hypothesis clear. Now, statistical hypothesis. To scientifically test the researcher's hypothesis, a formal structure is needed, right? Some formal structure, some formal, you can say, steps are needed, right? These steps are called statistical hypothesis, or you can say this test can be done using statistical hypothesis. We call it the steps or the structure is called statistical hypothesis. Okay, there are two types of statistical hypothesis, and this is what we need to learn more. The earlier three are, you can say, more or less theoretical concepts, but this is what we need to learn actually, and this is how you actually test the claim using null and alternate hypothesis. Okay, so two types of statistical hypothesis: null and alternate. So let's first understand what is null hypothesis. It's an assumption about the value of a population parameter, right? It is an assumption about the value of population parameter. It is usually the assumption with no change, means as is situation is my null hypothesis. For example, in my, again coming back to that example, marketing expenditure, or I company is planning to increase the marketing expenditure and expects the profitability to increase from 25 to 30%, right? So what will be the null hypothesis there? As is situation, situation which with no change, which is the current situation. Yeah. So what will be my null hypothesis in that? Profitability is equal to what? 25%. Right? Clear? Is that clear? That example is clear? Right? Profitability is equal to 25%. Okay. So it's a condition with null condition exists, means no null. It's a null, means as is. What is already there? No change. Right? Nothing new is happening in that state. In null hypothesis, nothing new is happening. Old theory is still true. These are some of the words you can associate null hypothesis with, and sometimes you might find these words in the text also when you maybe get some text to around the situation, right? Okay. Old standards are correct. Means the old standards that are there, they are correct and they are still existing. System is in control. Whatever is the system, it's still in control as is. Assume no change. Okay, and you write null hypothesis by H0. H with a 0. It's called, sometimes it's called H naught. Okay. Okay, question. Will the null hypothesis be profitability is equal to 25, or the profitability will not increase by 30%? No, 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 no. Not necessarily that it will stay the same. Yeah, yeah, just hold on, Angela. Next slide will clarify, will give you a clarity on it, right? Just hold on, right? Okay, this slide is clear to all of you? Okay, next. Null hypothesis must contain the condition of equality. Always. Null hypothesis will contain the condition of equality. It could be equal to, it could be greater than equal to, it could be less than equal to. Okay. So it must contain the condition of equality. When I construct the null hypothesis, it could be either equal to, less than equal to, or greater than equal to. Right? We're going to see the examples for all of these. Okay. Generally, the researcher don't believe in null. Now understand this statement. When you construct when you want to prove a claim, right? Coming back to that 25 profitability example, right? I am expecting, Angela, now listen it, right? It will answer your query also, right? I was saying, due to some changes in my company, maybe increase in marketing expenditure, I am expecting the profitability, which is currently at 25, I am expecting it to increase to 30%. So what am I expecting? What is the claim I am expecting? Increase? No, don't be vague. Don't be vague. Increase to 30%, right? If it increases to 29%, is it that I was expecting? Yeah, increase by 5% or increase to 30. But let's talk in terms of two, right? Increase to 30%. So now my next question is, if it increases by if it increases to 29%, was that I what I was believing? No, right? So what was my belief? Increase to 30%. Okay. So now coming to Angela's question, Angela. So when I'm saying increase to 30%, so my null H0 will be less than equal to, right? Uh, sorry, my H0 will be a condition which is not equal to 30%, right? I have to, what is the claim I have to test, right? I have to test the claim of 30%. So my H0 will be 25% equal to, wait, my H0 will be uh, less than equal to 30%, right? And okay, less than equal to, as is situation. See, I want to test whether what I want to test. I want to test. Yeah, right. Isn't this as is situation less than equal to 30%? Correct. It's 25. You're right. Right. Does 25 fall into this? Yeah. So we want to reject 25. Okay. Let me put it. Yeah, is equal to 25%, right? But and okay, let's put it H not equal to, which is the current situation, 25%. Okay, let's put it this way. Okay, right? So this is my H0 as a situation, right? Okay. Generally, the researcher don't believe in null. Means the researchers do not believe in null, or the data scientists when they are constructing a hypothesis, they do not believe in null. Means they are believing that next year 25 will not be there. Okay, right? Observed difference between the sample and population arises because of random chance variation. I will explain this in the next slide, right? So let's park this point for a minute, right? Observed difference between sample and population mean arises because of random chance variation. In fact, I have shown you this in that simulation, that whenever I take a sample and I take a mean, observed difference between sample and population, there was a difference. I'll show it again. There was a difference in the actual mean. Actual mean is this, and sample mean is this, right? So what I'm saying is, this is my population mean, blue line, and this is my sample mean, right? Okay. So there is a variation. This is called random chance variation, which I will explain shortly, right? It's because of random chance variation, right? Now we either reject H0. Now what we do is, when we test the claim, we say we are going to either reject H0 after testing the claim, or we are going to say we fail to reject. Now this is again a very important word, fail to reject. We never say we accept the null. If the conditions don't, the claim that I want to test, if I'm not able to test that claim, right, I will not say I accept the null. No, I will say we fail to reject the null. Means my current situation, I did was I trying to prove the current situation or the new situation? What was I trying to prove? New situation, right? I never i never tried to prove the as a situation, right? So I will say, okay, whatever is there, I fail to reject this because I could not prove the current new situation. Are you getting this? Fail to reject is a very important concept, and we will be learning it in detail, right? But for now, just understand this. We never say we accept null. We always say we fail to reject the null. So it's a double negative. Okay. Next. So these are the three types of hypothesis I've already told you, right? Okay. Next. What is random chance variation? It's an inherent error in any predictive statistical model. It is defined as the difference between now understand this very well. Difference between the predicted value of a variable by a statistical model in the question and the actual value of variable. Predictive value means coming from the sample, right? It is the difference between the value that is coming from the sample and the actual value of the variable, which is actually the population mean. Okay. For a fairly large sample, these errors are seen to be uniformly distributed above and below the mean. Do you get this? Let me go back to this. For a fairly large sample, 25 or 20, can you see these errors? Errors means the difference between this number and the mean, population mean. This number and the population mean. This number and the population. Can you see they are fairly divided on both the sides of the mean? Yes, they are fairly divided means equally divided on both the sides of the mean, uniformly distributed above and below the mean, and cancel each other out. Now, if I calculate the difference between each value and the population mean, I can see some of them are lying on left side, some of them are lying on right side. If I calculate the difference, they are going to cancel out, right? That is what it is saying, resulting the expected value to be zero, expected value of the variation, expected value of the difference, right? So nearly, or we are going to, if I now if I take a sample of n equal to 5, right, this might not be the difference on both the sides. I might end up in a bigger difference because the sample size is small. But if the sample size is large, 25, right? Because these samples are coming randomly. So approximately half of them will be on the right side, approximately half of them will be on the left side, right? And hence cancelling the mean. This is called random chance variation. Okay? Okay? Is this clear? Fairly large sample, these errors, for a fairly large sample, these errors are seen to be uniformly distributed above and below the mean and cancel out, resulting in expected value equal to 0. Is this clear? This is clear? Now let's take another example to understand this, some more examples. I I think I discussed this also when we discuss variability. Again, the same example. I ask all of you to go from city A to city B. I give you the same car. You start at the same time, right? So when you will reach, and I take a average time you have taken. Some of you will be less than mean. Some of you will be more than the average, right? Isn't it? Some of you will be going, I mean, moving faster. Some of you will be moving slower at a comfortable pace, right? So when I take the difference of all the data points from the mean, right, it's going to end up in 0, right? That is called expected value, right? Clear? Second, if I take a pulse rate of randomly 500 people in a locality, do you think the pulse rate of all of them will be exactly the same? There is going to be some random chance variation, okay? And this random chance variation is inherent. That is why it said it is the inherent error. It should not impact. Now, this does not impact my model, right? So this should not impact my model. So it is inherent, which cannot be removed. It is because of the randomness that exists in the world, because of the randomness that always exists. Okay, clear? Random chance variation is clear to all of you. The factors influencing the behavior of a variable in question usually behave in a random way, right? The factors affecting usually most of the variables, they behave in a random way. So the outputs and the resulting so the outputs and the resulting chance errors also appears in somewhat a random fashion. The chance errors, random chance errors, right, cannot be controlled. You cannot have a control on these. However accurate the model be, the presence of this error hence does not reduce the credibility of the model. So whenever I'm going to test the claim and after that I'm going to create a model, right? This random chance variation will always exist. It will not be, you cannot control it. It is inherent error. Is that clear? Random chance is clear to all of you, right? Now coming to why fail to reject. Why do we say fail to reject? Though I have given you we have had a small discussion on it, but yeah, let's have a fail to reject sounds like a double negative. We cannot conclusively affirm a hypothesis. But we can conclusively negate it, right? We cannot conclusively affirm something, but we can always negate it. I'll come to this, right? We assume that the null hypothesis is correct until we have enough evidence to suggest otherwise. Are you getting this? So we just assume whatever is there that is correct until I have something to prove otherwise, right? The fact is that we cannot prove a negative. So it's like we cannot prove a negative. It is absence of something is negative. Okay, right? Absence of something is negative. It is not that we don't have to prove negative. Okay, A lack of evidence only means that you have not been able to prove something, and that is what happens in court trials also. I'm sure all of you know court trials. I'll just discuss it in the next slide. Okay, criminal trials, right? A lack of evidence means we have, even in the court, the person, the prosecutor, what does it say? We were not able to prove the criminal guilty, right? They never say the criminal is innocent. We never say this. We could not gather the evidence and we were not able to prove the criminal guilty. Okay, clear? So lack of evidence only means that you haven't proven that something exists. Okay, it does not prove that something does not exist. It might exist, but your study missed it. Clear? Fail to reject is clear to all of you. Why do we say fail to reject? Any confusion on this? Let me know, because these are fundamentals, and I've seen people, they get into that habit of, okay, we reject the null or we accept the null. They just get into that vocabulary, which is wrong. Okay, we never say reject. We accept the null. We say we fail to reject the null. Okay. Okay. Example of criminal trials. We all know how do we start. We start with the assumption that null, that criminal is not guilty. H not. We always start with an assumption that it is null, right? Criminal is not guilty. Okay, unless proven guilty. Unless, now bring evidence, prove him guilty, then only we will prove, then only we will say he is guilty. Otherwise, he is not guilty. He is not, I'm not saying he is innocent. There is a difference between not guilty and innocent. Clear? Prosecutor works to prove the criminal guilty. He brings in evidences. If he is not able to prove the criminal guilty, the verdict says not guilty. The judgment does not say the the defendant is proven innocent. Just that there wasn't enough evidence. The the criminal was smart enough to be able to hide all the evidences, and we were not able to prove it. Okay, is this clear? Why we say fail to reject? Okay, so null hypothesis. Now coming to alternate hypothesis. It is what is believed to be true. We believe it to be true. Now we have to test it, right? So when we believe something to be true, that is what is alternate hypothesis. It's a negation of null, means negation of the null, right? Means not the null. In this, the alternate hypothesis state new theory. Alternate hypothesis states the new theory is true. New standards are there. System is out of control. So these are some of the words that are associated with alternate hypothesis. Something new is happening, and statistically significant change is observed. Now, again, a very important term, statistically significant. I'm going to discuss that in the next slide or coming slides. Okay. Statistically significant change is observed. Now, what is a statistically significant change? We'll see. Okay. And it is represented by H1, or sometimes you will find it HA also. H with a small a or a capital A. Sometimes it's written like this, H A or H capital A, but a subscript. Okay. Okay. Criminal is guilty can be an alternate. Yeah, it is. Criminal is guilty is an alternate. Okay. Criminal is not guilty is null. See, criminal is not, when, how do we start? Not guilty is null, Nutan. Okay. See, we start with as is. Criminal is not guilty. What can you assume? You, what is as is situation? Till the time you have proven it, can you say he is guilty? He might have done 100 criminal activities previously, but for the activity you are putting him on trial, is he guilty? No, right? So we will say as a situation is criminal is not guilty. Okay, it's H0. Okay, and when we prove it, right, and that is, what we want to do, we want to prove him guilty. So criminal is guilty is my H1. Clear? Okay, clear? All of you? Right? Okay. Now let's see. Okay, yeah. No, some more things about alternate. Now this is also a very important slide, especially to understand alternate hypothesis. It must be true if H0 is false. So I am taking only two states, right? In my profit example, I am taking 25% profitability and 30% profitability. It could go on the other side also, right? There are many other states, but I am testing only 30%, right? So what I'm testing is alternate hypothesis. It must be true if H0 is false, okay? Does not contain the condition of equality. Everyone agrees, right? So these three could be my alternate. Not equal to 5, less than 25, and greater than, right? Not, basically equality will not come in alternate hypothesis. Negation of null, already told that. Usually what we are testing, so it is what we are going to test. Of course, I am not going to test my as a situation, right? Claim we are testing, or the initial claim that is to be tested, that is called alternate hypothesis. Okay, so as a data scientist, you are interested in testing that a change is expected or not. Okay, and that change situation, that new situation, is the alternate hypothesis. Okay. Okay, now let's see some examples. Things will get more clear as we see these examples. A company has held a 23% market share of product A. There was an increase in the marketing effort. Hence, the company believed that its market share is now greater than 23. Okay. Yes. Tell me what is null here. Null held a market share of 23%. Exactly. Right? Held a market share of 23%. Null as is situation Vaibhav. Right? Now, company believe that its market share is now greater than 23. So, what is alternate? Okay, Nutan, here we are testing on, see, we are testing on greater than, right? So, my null is going to be less than equal to 23. My fault. I just missed on that. My null is not going to be equal to y. See, if I read the first statement, it looks like equal to. But when I read this, what am I testing? What am I testing? Greater than, right? So this greater than is going to help me even understand, put the null also, right? My test, I am testing that my market share is going to be greater than 23 or not, right? Alternate, you can get alternate very clearly, right? Put everything else in null. First you identify the alternate and then put, and this is what I, when I said initially 30% market share or profitability, right? But then I wrote less than equal to 30%, right? But I took it as 25 because I did not explain this concept there, right? See, first you have to identify what is the change. I am expecting it to be greater than 23%, right? So that is my alternate. Very clearly. Now put everything in null, and of course equality has to be there. Is that clear? See, isn't this my, even if I am holding 23% market share, isn't it coming in this? Isn't it coming in this? Less than also, right? Clear? Okay, clear? How do you construct null and alternate? Is that clear? Let's take a look at another example. Now, notice that here, my alternate is on one side, greater than the, it's not on the other side, it's on one side. Okay, so we call it one tail. We'll discuss one tail also, but for now, notice my alternate is on only one side. Okay, okay, next example 2. Yes, a retail store wants to test if the average age of its customer is less than 40 years. So what he wants to test? What is the claim? Less than 40 years. That is going to be my, it does a survey, right, to gather the data of the age of customers, right? So what is the, my alternate is less than 40 years, right? See, and my null, everything is else is null. Correct, Nutan, right? Exactly. What is to be tested is alternate. Yes, Nisha. That's the crux. And if I take you back again, claim we are testing or the initial claim. Usually what we are testing is alternate, right? Sometimes if you start identifying the null, right, first, it gets confusing. Like here, right? You might end up in a wrong null. But if you start with alternate, it will become easy. Just remember 2, 3 conditions. Equality cannot be there in alternate, and then you start, and it is something, alternate is something you have to prove. These two, if you remember these two statements, you will be able to construct the null and alternate correctly most of the times. Okay, clear? Example 2 is clear. Let's see example 3 now. Yes. The hypothesis is conducted to test if the population mean is still 100. Okay. Notice the words. Population mean is still 100. 25 samples are corrected and the sample mean was 103.2 with sample standard deviation of 10. Okay. So what we have to test? First of all, tell me what we have to test. Is still 100 means exactly it can change either ways, it can go either ways. I am just testing whether it is still 100 or not. So what is my h0? What is my h0? Exactly, right? And h1 not equal to. Clear? So we have done all the 3 cases. Now notice that here the change can occur on either side, left or right, right? So we call this a two-tailed. If we are, when we are testing the change, when we are testing the change, whether the change will occur on either side, right? It's called two-tailed. Okay. And when we are testing it on one side, we call it one tail, whether that be left or right. Okay. Clear? So this Example 2 is a case of one tail. Example 1 is also a case of one tail. We are just testing it on testing. We will be testing on one side. Okay. Clear? Next, why perform statistical hypothesis testing? Now, why do we do this hypothesis testing? Hypothesis test is a form of inferential statistics with which we draw conclusions about the entire population based on a representative sample. A representative sample is something which is random, means you just collect random samples, but the sample should be representative. It should represent the entire population, right? It should have as many features of the population as possible, right? Then only it will be representative, right? There are a lot of benefits by working with samples. Yes, that is why we do hypothesis testing. There are a lot of samples. Model build is correct or not? Yeah, right. So there are a lot of benefits. What are these benefits? In most cases, it is simply impossible to observe the entire population to understand the properties. We have seen this in many a times, starting from the Coke example, right? We have discussed this many times, so I am not discussing this. Alternative is to collect random sample and use statistics to analyze it. So I cannot collect the entire population sample. I cannot collect the data from the entire population. So alternative is I collect a random sample, which is a representative sample, and use statistical technique to analyze it, right? Also, samples are much more practical and less expensive to work with. Of course, the resources that are going to apply are going to be less, right? There is a trade-off to work with samples. When you estimate the properties of a population from a sample, the sample statistics are unlikely to be unlikely to equal the actual population value precisely. We saw this. It will not be precisely equal to a sample from a sample statistic, means a sample mean. It will not be precisely equal to population. There can be sampling errors, which I just showed it to you. The difference between the sample statistic and the population value is called sampling error. Now, when I pick up a sample, now this the sampling error is less if my n is bigger, but sampling error can be more if my n is small. Okay. See, you can see with a single sample, you can see the difference. Take n equal to 5 and take n equal to 25. The error is going to be far lesser. And even though it's a random sample, error will be far less when we are taking n equal to 25. Okay. Difference observed in samples might be due to sampling error rather than representing a true effect of the at the population level. Different samples will show different results. Of course, if I take different samples, they are going to show different results. They are not going to be exactly equal in to the population mean, but they will also have different errors also, right? Hypothesis testing incorporates estimates of sampling error to help you make the correct decision, right? Incorporates estimates of the sampling errors to help you make the correct decision. Okay, so that is why we perform hypothesis testing. Substantive hypothesis. Okay, another type of hypothesis. Let's understand it, and it's primarily statistically significant explanation of statistically significance. See, when it comes to business, okay, first let's read this. Statistically significant results are not always business significant outcomes. See, let's say, let's talk about the 25% and 30% profitability, right? I am spending millions of dollars, right, in that program or in that to bring that structural change so that I'm able to increase the profitability from 25% to 30%, right? But actually what happened, my aim was to increase it to 30%, which was significant for me. It was business significant, right? Yes, business wants it, so we are spending millions of dollars. But what happened actually, because of some unforeseen factors, my profitability increased from 25% to 25.5% only. Understand this. It increased from 25% to 25.5%. Do you think this is a business significant outcome? Is it very significant for a business? No. But because of some factors, because of some factors impacting my model or impacting the situation, it is still a statistically significant result, isn't it? It increased to 25.5. It is a change, and there might be some more variables which uh, impacted my situation, which initially I would have not thought. That I thought that okay, these variables were will not impact, so my profitability will increase to 30%. But there were some variables that impacted, and my profitability increased to only 25.5. So it's a statistically significant change, but not a business significant change. Is that clear? Example is clear. Business significant and statistically significant. Now, second statement is again a very important statement. Two statisticians, or of course a data science, two data scientists. You can read it as data scientists, right? The word significant means the results are not merely due to random chance. Okay, there were some additional variables, but it is not, the results are not because of random chance. Okay, they are because of some model, because of some variables impacting my dependent variable. Okay, that is, we reject the null hypothesis. Means we, of course, even with 25.5, I am going to reject my null, right? Which is h naught equal to 25. Null will be rejected at that also, right? Clear? To business decision makers, substantive result is when the outcome of the statistical study produces results that are important or large enough for them, right? Now, for them, substantive result is comes when the statistical study produces the results that are important to them or large enough. Large enough, we have seen an example, right? Now, important. It could be important to them also. For example, an example of important. What should I take an example of important? Okay, let's say in a city there was a government uh, man, government has made mandatory that there should be 25% females working. I'm just cooking an example here, right? That 25% females should work in any organization, right? Now, right now, my the percentage of women working in the organization are 24.5, right? But I have to meet that 25% criteria. So next year I'm planning to increase the percentage to 25%. So I'm planning to increase it from 24.5 to 25%. The change is again very minuscule, right? zero point 0.5. But it's an important change because I have to meet the government guidelines. Are you getting it? Right? So that's an example of important. It could be important or large enough. Large enough, we have seen the example. For them, they focus on ROI. Business is focusing on ROI, right? That is why 25.5% profitability was not, the business was, for them, it was not a significant change because They are planning to, they have spent millions of dollars, and the raise they got is only 0.5% profitability. That is what they were not eyeing, right? Clear? So that was because they focus on ROI, right? ROI means return on investment. So they are saying we are we are spending millions of dollars, so we are expecting at least a 5% profitability increase. Okay? Okay. Statistically significant. Yes. Statistically significant means that the results or outcome of an event likely did not happen by random chance. We have discussed this here also, that it does not, the, the change did not happen by random chance. It was some model, there were some variables which were impacting my independent variable, or sorry, dependent variable, right? It did not happen by random chance. Means test results are significant or meaningful, right? Statistically significant means test results are significant or they carry meaning. It's because of the change in independent variables. Correct, Nutan, you're right. Right? More specifically, whether your statistic from sample closely matches what value you would expect to find in the entire population parameter. Okay. More specifically, whether your statistic closely matches what you are expecting or not, right? So that it tests that, right? It it signifies that, right? Means that we have evidence that the result we see in sample also exists in population, right? So means that we have uh, the evidence that the results that are coming from sample also exist in population. That change that we are seeing in the change that we are seeing in population is represented by the sample also, is also seen in samples. Okay. For example, 120 people from a city were asked their sports preferences, right? You would want the sample results to represent everyone's preference in the city, right? In other words, you would want the report to have statistically significant findings. Means when a sample is representing, when the change in the population is represented by a change in the samples, change in the sample statistic, it means the results are statistically significant. Clear? Okay. Okay. Now coming to errors. Very important again. Errors. So since we are dealing, we have to prove a claim, right? We have to prove something, some statement, right? Or in terms of court trial, we have to prove a criminal. Can we be 100% correct always? Can we be 100% correct always? We are not God, right? Even the best of the scientific techniques, they cannot be 100% sure in this world, right? Whatever. You can increase the probability of success, you can increase the chances of success, but you cannot be 100% sure every time, right? Clear? So, because, yes, right? So, there will be some errors that you can make, right? There will be some errors. There can be some errors, not will be, there can be some errors. What can be the errors? Now, let's understand the errors that we can make while we are testing the claim with the help of this matrix. Actually, the H0 was true, right? Now, this is a situation. See, if we test a claim, what can happen? Either H0 will be true or H0 will be false. That can only happen, na? Right? Either as when H0 is true and we are rejecting it, but the proofs that we collected or the uh, claim that when we tested that claim, we said we are going to reject H0, right? So actually what happened? H0 was true, that no change happened, but our tests say that a change happened, so we reject H0, right? Okay, we made an error here, right? This is called type 1 error. This is called type 1 error. Rejecting a true null hypothesis is called. You can by heart this statement if we have to, and we will be doing this errors. I mean, till the time you are doing inferential statistics, which is actually a foundation of modeling, right? You will always come across this alpha and beta. These are standard statistical notations. Okay, alpha means type 1 error. And what is the type 1 error? Rejecting a true null hypothesis. Can you give an example of rejecting a true null hypothesis? Can someone try and give me an example of rejecting a true null hypothesis? Okay, let me give an example. I am expecting today is a sunny day, so I am expecting no rains, right? And so what is my I am expecting no rains. So H0 is no rains. H1 is, but when I go out, right? Sorry, yeah, today is a sorry. I'll just repeat the example. Yeah, market share. Okay, let's talk in terms of market share. Let's take, yeah, no rains is null. Correct. Okay, so no rains is null. Okay, right? But I am when I in the evening I went out and I was expecting that rain will occur, right? But rain did not occur, right? Actually, the rain did not occur, but I carried the umbrella with me, right? So when I carried the umbrella, I rejected the null, right? So what was the consequence? That I have to carry an umbrella even though it did not rain, right? I made an error, right? Right? I made an error there. Okay. So rejecting a true null. It is also called false positive. Patient is not, okay, Newton says patient is not having COVID, but RT-PCR is positive. Yes. Patient is not having COVID. Yes, right. Right. But RT-PCR shows it is positive. So it means that RT-PCR is wrong. Right. That there is an error in that. Okay. Right. So rejecting a true null. Okay, second type of error that we can, okay, now will there be an error if I say H0 is false, that H0, I am expecting a rain will occur and I carry an umbrella. Will there be an error? No, no error, right? So that is called true positive, right? I am expecting a positive change and it is true also, right? So true positive, and this is represented by 1 minus beta, right? We'll come to this 1 minus beta. First, let's understand this second type of error that you can make. First error we have seen, H0 is true, null is true, but I am saying, but I am rejecting null and I am carrying the umbrella. I am rejecting the null and I'm, right? And I am expecting a change. Okay. Now what is the other error? H0 is false. Actually, the change is happening. Umbrella. Oh, sorry. Rain is going to happen. Rain happen in the evening. But I was confident it will not happen, so I did not take the umbrella. Right? Okay. Exactly, Vaibhav. You are correct. Right? It's raining, but I did not carry the umbrella, thinking it will not rain. Okay. So it's called false negative. So what we are doing here, we fail to reject null, false null. Notice, fail to reject false null. I am sticking with the false null. I am failing to reject the false null. I am thinking wrongly. I am thinking that there will be no rain, but actually the rain occurred. Clear? This is called beta. This second type of error is called beta. Okay, two types of error is clear: rejecting a true null or failing to reject false null. Is that clear? Rejecting a true null or failing to reject a false null. Okay. Being optimistic is beta error, right? In fact, even beta, yes, you're right. In fact, beta is more dangerous also, right? The error beta is far more dangerous than alpha, right? Yes, you agree? Just think the two situations in terms of umbrella. Which is more dangerous? You carried the umbrella when it was sunny or it was not raining, or you did not carry the umbrella and you get wet in the rain. Beta is always more dangerous. Even in terms of COVID also, when you see, we'll take an example, right? We'll just see the example. Okay, clear? Right? Now, when you are, okay, when H0 is false, actually, and you reject H0, right? H0 is false and you reject the H0. It is true positive, right? You are expecting, actually the change has occurred and you are also rejecting the null. Means you are expecting the change to happen. It's called true positives. And this is also called power of test and specificity. We'll come to specificity later. But for now, just understand this is also called power of test. 1 minus beta is called power of test. Remember this. You might be tested on this even in the interviews also. What is the power of the test? Okay, 1 minus beta. Okay, negative, true negative. Yeah, H0 is true, right? You are saying no rain is going to happen and you did not carry the umbrella, right? So, true negative. This is called confidence level, confidence coefficient, or sensitivity. Again, sensitivity will learn later. For now, understand this is called confidence level, right? Isn't it confident? Yeah, you were saying optimistic, right? Is I am optimistic and my optimism was correct, right? So being optimistic is not a beta error. Being optimistic when the situation is not in my favor and being optimistic there is a beta error, right? Yeah, you can say being optimistic, of course, when the situation is going to be otherwise, right? Okay. So okay, now coming to, so the two errors are clear, alpha and beta. The errors are clear to all of you? Errors, right? Okay, let's look at the differences in the two errors. Meaning, it's a non-acceptance of a true null, right? Rejection of true null, right? Non-acceptance. Acceptance of a false null, right? False null is there, right? I am accepting a false null, right? Actually, it was H1, but I am accepting a false null. Again, a mistake. It's called beta, right? What is it? False positive. It is false negative. Okay. Represents a false hit, and this represents a a miss opportunity and hitting a wrong opportunity. Okay. Clear? Probability of error. Now, this is also called level of significance. Did I mention it there? No. A very important term you will come across. Alpha is also called the level of significance. Okay. And this is called the power of the test. I think I mentioned level of significance. No, I did not. This is called the level of significance. Okay. We are going to discuss level of significance also. Clear? This is called level of significance and this is called power of the test. Clear? Examples. See, A new drug is accepted, but it is not effective. See, the drug is not effective, but we have accepted it, right? Clear? Rejecting a newly effective drug. Now think even here in these two examples, which is more dangerous? Just think in COVID terms. Rejecting a new effective drug or a new drug that is or new like vaccination, right? Which is not effective. I I was coming up with a new vaccination, but we rejected a new effective drug, right? Will that will be more dangerous, right? Okay, okay. Another example of bank customer, I would want you to go through it. This rain example I already discussed, right? It's the same thing, umbrella and rain. Bank customer, you can go through this. Now coming to the steps of hypothesis. Let's take a break. I think this step I want to do it in continuity, right? We'll take a break. Or okay, let's do this. Let's understand this example, right? This is also a very interesting example. We'll understand this in 2 minutes and then we'll take a break. Okay. Okay. Now, when you go to a bank, right, you fill some forms. You suppose you went to bank for a loan, right? You fill a form, right? You fill a form. Bank collects detail. Do you think they are just collecting it for fun? No, they are not collecting it for fun. They use that data to and the data that is collected is scientifically collected. Means they are collecting data of the variables that are very important for you. Sorry, that are very important to be able to predict whether they should be giving you loan or not. Okay, it's not collected just for fun, or maybe they just randomly on a morning they wrote, okay, let's collect these variables. No, 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 no. It happens very scientifically. Okay, okay. So when you go to a bank to take a loan, bank assumes that you are a good customer, right? Okay, they assumes you are a good customer until proven wrong. You are a good customer for them. Okay, so H0 is a good customer, but when they collected the data, let's say the data they collected, you already had heavy loans. You have, let's say, your income was not smooth, right? So all this, so they rejected the customer, right? Whatever data they collected, sorry, whatever data they collected, they rejected that we are not going to give a loan. But actually, okay, the loans were very large, right? So they did not take a look at the income, but they found the loans already. This person is carrying 3 loans, right? Okay, so they rejected, but actually his income was in crores in month. So he was he was a good customer for them. He had a very good income, so he could easily manage 4, 5, even 10 loans, right? His income was in millions, right? Okay, so customer was good, but when the bank rejected the customer, they made a mistake. That's a type 1 error, rejecting a true null, rejecting a good customer. Okay, what could be the other error? They The customer was bad, but they found it to be good. Their analysis, their data said it was a good customer. Now what will happen? Again, see here, beta is more dangerous. Bad debts are going to happen, right? The person is going to be taking up a loan and will not return. He's a bad customer. But bank said, okay, it's a good customer and they gave him a loan. Okay? Clear? Type 2 error? Okay, is this clear? Type 1, type 2 error is clear to all of you? Now we'll take a break and we will understand the steps in hypothesis. Post the break, hopefully you have You are enjoying the session, and you are enjoying this learning, and you're learning, of course. Oh, sorry. I'll create a poll, right? Please do participate in the poll. Let us know how did you do in terms of pace and delivery. And the poll is open now. Okay, and will come in 20 minutes from now, right? I'll put up a timer for 20 minutes. Please do come back as per the timer. No, I don't take Python. Uh, okay, so I'm putting up a timer. Please do come back as per the timer. Thank you so much. Appreciate your interest, your participation, and hopefully this session has added value to all of you. So timer for 20 minutes. I put up a timer for 20 minutes, and Okay, Nutan. 1 minus beta is the power of test, not beta. Okay. Did I say power of test? This is no 1 minus beta is the power of test. Okay. This is it should be 1 minus beta. Okay. Okay. Can we start the steps of hypothesis quickly, and then we'll move over to the. Okay. I've really gone slow because with this hypothesis testing, because this is a conceptual. I mean, it requires a lot of conceptual understanding, right? So today we'll finish this hypothesis test and we'll start with Z test today. Okay. Okay. So there are some steps in hypothesis. Three of the two steps we have already done: setting the null and setting the alternate. Step one, step two. Step three, setting the alpha level or the significance level. Right? We know what is alpha and how do you test? How do you set it? We'll see. Then selecting the distribution test, which test need to be performed. There are different tests. Which test need to be performed? We'll see that, right? So we have four types of tests in our curriculum: Z test, T test, ANOVA, and chi-square. Okay, so we'll see which test can be performed when needed. Okay. Then just a second. Okay. Then calculating p-value. We'll see what is p-value and how do you calculate that, and then how based on p-value we take the decision. Okay. Then last is taking the decision. These are the six steps we are going to. We have done these two, and we'll start with the next third step. So this is first is setting the null, setting alternate. We know how to do that now. Third step, setting significance level or alpha. Now, what is alpha? I've already explained what is alpha. It's the error, right? The chances of type 1 error, right? Now, we also define significance level. Alpha is the maximum probability of accepting a type 1 error, right? That is how much error am I willing to take? How much? See, as I said, we are not God. So, we can increase the chances of our uh, increase the chances of success or reduce the chances of error, right? Or in other words, we can say that okay, I'm ready to take up. I'm in my experiment that I'll do or in my test that I'll do. I know it can't be 100% correct, so I'm willing to. I'm okay to take up this much error, right? There is going to be some error. There will be a chances of some error, right? So I am willing to take up that error. That is called alpha. It is the type 1 error. I am willing to. I know that the data I'll collect, it might not be 100%. It might not give me 100% correct results. I am willing to take this much error, right? That's and the error that I am willing to take is alpha, right? So there are three levels in business, right? There are three levels on which we test the we three levels of alpha that we accept, right? That we take rather. 1% level when I really want to be very stringent on my tests, right? Usually happens when medical cases, right? Usually happens when there are some medical cases or some cases related to safety, right? Car safety, right? The features that we install, they are tested, right? So at a very stringent level, they are tested, and we are we in such tests we accept only a very limited amount of error. I mean, the least amount of error we accept, and we that is 1% error. Okay, then 5% is the most usual. Whenever even in we'll be doing some questions, we'll be doing some discussing some cases. Whenever nothing is mentioned, 5% is the most reasonable error that you can accept. Okay, and then you have the 10% error where you are not that stringent. You are, I mean, liberal on the errors. You can take, you are ready to accept 10% error. Okay, clear? And another very important thing here is, so if this is my normal curve, so this is my area under the curve, right? The area under the curve is 1, right? So this is 1%, okay, error. This is 5% and this is 10% of the error. Okay, right? Now I was saying, yeah, when I say 1% of the error, I am ready to accept 1% of the error, right? So how much confident you will be about the about that my test is going to be correctly uh, supporting the claim, right? 99% error, right? So confidence level is equal to 1 minus significance level. Always remember this. 1 minus alpha is the confidence level. It is the probability with which we accept the null when it is true. Of course, right? That is what I mentioned here also. Confidence level. Probability of accepting a true null hypothesis, right, is called confidence level. Okay? Okay. These the selection of significance level depends on the business case of how stringent we want the test to offer assumption with. I've already mentioned this, right? Clear? Significance level is clear, right? Now, one tail and two tail test. Now, I've already discussed a bit on one tail, two tail test, right? So, whenever I am testing a claim of equality, right? I want to see eating a burger takes 10 minutes, 10 minutes time, right? Example, eating a burger takes 10 minutes time, right? So, I want to test this claim, right? So, is this a one tail test or a two tail test? Two tail test, because I am Weber, why one tail? Two tail, right? Equal, I'm saying eating a burger takes 10 minutes, right? So, what am I going to test? Whether time taken is less than 10 or more than 10. That is my alternate, right? So, it's a two tail test. Error can happen on both the sides, right? The claim I'm going to test, error can happen on both the sides, right? I am saying that it's a that you took that average time taken is 8 minutes, but actually it was not 8 minutes, right? That can be one error. Other side, I am saying that the time taken to eat a burger is 12 minutes, but actually it is not 12 minutes. So error can happen both the sides. That's a two-tail test. Okay. So for two-tail test, the total level of significance is split into two. Suppose I want to test the claim that eating a burger takes 10 minutes time at a 10% significance level, right? So on both the sides, I will have zero point 0.5 alpha by 2, zero point 0.5 alpha by 2, right? And this is going to be my 90%. 1 minus alpha is 90%, right? Okay, clear two tail test and one tail. The wherever we are testing only the claim, I want to test again the time taken to eat a burger is at least 10 minutes. right? So what am I testing? At least 10 minutes, right? Or now let me put it, is more than 10 minutes, not at least 10, more than 10 minutes, right? Yeah, more than 10 minutes, right? So what am I testing? Time taken is more than 10 minutes. One tail test. Okay? Clear? So in that the entire error can happen only on the one side. Whether this it can be left tail or right tail. It can be either. Right? One tail can be left tail or right tail. Right? Okay. Next. Now this region critical, this is called region, critical region. The critical region is the set of all values of the test statistic. What is test statistic? We'll see. Right? That would cause a rejection of a null hypothesis. Means if this is the error, zero point 0.5 is the error I am ready to accept. Right? Now understand this. I am ready to accept 0.5 error. Right? Up to 0.5 error. Right? But when I did the test, my error came out to be 0.3, 0.03, right? 0.05 is this. My error came out to be 0.03. It means the the new situation isn't that much more conducive, much more beneficial. It is carrying less amount of error. Yes. So what will I do? I will reject null or I will accept null. Why? Accept null means, see Arush, accept null means you are going with the as is situation. I am saying when I calculate the new situation, the error came out to be 3%. I am ready to take 5% error. So isn't it a better situation, Arush? So I will reject null na and go with the right. So think it that way, right? I know you have to think on it's lot. This concept comes with a lot of twists and turns. So just concentrate on the words. I also have to choose the words. Sometimes the words also slip at times, right? If I just go fast, sometimes the words also slip. So you have to just think what I'm saying, right? Just understand it. I I got it. Everyone got this? What I said? So this becomes my critical region, means it is the region, critical region is the region in which I will reject the null hypothesis and accept the alternate hypothesis, right? So when my error comes, if my error comes to be 3%, but I am ready to accept 5% error, right? So I am going to reject the null, right? Clear? This point is clear. So this is called critical region. Okay. Critical region is also called the rejection region because we will reject the null, of course, right? Okay, can we proceed? Next. Critical region, of course, can be again, as I said, it can be on one side or two side. This is pretty simple, right? We have already done this. Critical region, if I have to test the claim on both the sides, it will be on both the sides. Rejection region will be on both the sides. Otherwise, it will be on one side in one tail test. Okay, now coming to what are the different types of tests that can be there that you can apply, that you can conduct to do the hypothesis testing. Okay, if your if your population is normally distributed, you do these tests: z test, t test, and ANOVA, right? And if your population is not normally distributed, or it is discrete, or sorry, yeah, it's not normally distributed, right? We do chi-square. There are other tests which are not there in our curriculum, so we are not going to touch upon these three. Chi-square. So test, there can be z test produces a z score, t test produces a t score, ANOVA produces f statistic, and chi-square produces chi-square test statistics, right? So these are the four tests that we can conduct or we have in our curriculum, right? Now from these tests, a test statistic, a score comes in, test which is called test statistics, right? And we compare it. with the significance level. We use the significance level to come up with a critical value, right? And this critical value, so at this significance level, if I apply a z-test, there comes a value that is called a critical value. Okay, and that critical value divides the non-rejection region with that of rejection region. It's the same thing. Critical value is just the value of that error, right? Right now it is in percentage term, 0.5%, but what is the value of that? That is called critical value. So it also divides the region into rejection and non-rejection region, right? Now that value, critical value is compared to the actual error, right? This actual error, which is called the p-value. Now p-value is again a standard notation, right? What is p-value? Let's understand this, and then we will come up to how do we reject and accept, right? So what is p-value? P-value is the calculated probability of the actual event. Means, see, what is alpha as 5%? It is the error rate that I can accept, right? It is the error rate that I can accept, right? P-value is the actual error rate. See, one, you are assuming, okay, I will be able to accept this much error, right? Then when you actually do the test, when you actually do that experiment, or when you actually do that, when actually the event occurred, right? The error rate was something which is called a p-value. P-value is the calculated probability, means of the actual event. Okay, cumulative probability of all the outcomes as extreme or more extreme than the observed value arising by chance. So actually this p-value is the value of all the outcomes as extreme or more extreme than the observed value arising by chance. So by chance means actually when the experiment was conducted, this was my p-value, right? 3%, which as I said. So 3%. Just a second. 3% is my p-value, right? As I said earlier also, example, 3% is my p-value. So isn't this area under this tail, right? So cumulative probability, isn't this 3% a cumulative probability on this side, right? Cumulative probability of outcomes as extreme or more extreme, right? If this is my p-value, all these are more extreme. if 2% comes in, isn't that more extreme than 3, right? Yes, right? So cumulative probability of outcomes as extreme or more extreme than the observed value. My observed was 3%, but it is equal to all the values of as extreme or more extreme than 3. Okay. Sorry. It is area under the tail. I've already shown you. This is the area under the tail of the probability distribution. Now this is p-value is the evidence against the null hypothesis. Against the null means if my p-value is the probability of the error occurring actually, but actually my probability of the error occurring was 3%, but I am ready to accept up to 5%, and so I will reject the null, right? So smaller the p-value, stronger is the evidence that you should reject the null, right? Suppose you conducted 2 experiments. I am ready to accept 5% error. In one experiment or in one model, my error rate came up to be 3%. In another model, which was far better model, my error rate came out to be 2%. So which we are going to accept? Which one you are going to accept? 2%, right? Everyone agrees? lesser the error. So it is an evidence against the null. Against the null means I am going to reject the null. So smaller the p-value, stronger is the evidence that you should reject the null. Is this making sense to all of you? Correct? Okay. So also let's understand p-value in another in terms of risk. Let's understand p-value in terms of risk, right? Now, as I said, p-value is the actual risk that we are carrying in the model when the event occurs. So it is the actual risk. It is the actual probability of a risk of the event not occurring, right? Here risk means probability of type 1 error. Now risk is the probability of type 1 error, right? When we reject the true null, right? But I am saying now this is my accepted probability. Now is the probability that I am ready to accept. Oh, sorry, error that I am ready to accept is alpha, right? Significance level is the error that I am ready to accept. So I am ready to take up 5% risk in my model, but actually p-value shows that my risk is 3%, the example that I took, right? So we can also call it p-value. We can also call p-value as the actual significance level. Are you getting this? It is the actual significance level, no? Right? Actual risk. Significance level is the desired probability of type 1 error. That is the accepted level of risk, right? So significance level is the acceptable level of risk, but p-value is the actual level of risk. Okay, clear? When p-value is, of course, when p-value is less than alpha, what we'll do? Tell me now. It means actual risk in the model is less than the desired risk. So I'm going to reject the null, right? And we conclude that the change is statistically significant. Means the change that is happening is significant statistically. Okay, we reject the null. When p-value is sorry, when p-value is greater than alpha, means my model that I am testing is carrying more risk that I am ready to accept. Okay, so I'm going to what I'll say in this case, fail to reject. I will not say accept H1. I will say I will fail to reject. Remember that word, fail to reject, right? So we will stay with the status quo, will stay with the as is situation. And we conclude that the change is not statistically significant. Is this clear? P-value is clear to all of you? Coming to how do you take decision, I've already stated it here. It's the same thing that I've explained, right? Lower the p-value means lower is the likelihood. It means that it is less likely that such a sample that I have picked came from the population, right? Means I am more confident that such a sample came from a different population. Hence, we reject the null. Okay? It means my sample now there has been a change in the population, right? So it has become some new population. So the sample, I am more confident that the sample came from a different population, not that status quo population or the last year population. There has been a change in the population, right? For example, let's say uh, we were testing the obesity levels, right? What is the best and the most easy measure of obesity? Kgs, right? Kilos, right? Kgs, right? Weight, right? So last year for a city, the average weight was not last year. Let's say 5 years back, the average weight was 70 kgs, and this was going on. Now we want to test, right? We want to test whether the obesity level are still there or whether the population is more obese than the have become more obese over the period, right? We take a sample, right? And the weight of the sample came out to be 80, right? Now we did a test, right? So this 80, when the sample from the sample, when the new population, oh sorry, when the sample that I took, the new weight was 80, right? Suppose we rejected the null here, right? So this 80, now my population characteristics have changed, right? They were earlier 70, now they are 80, right? So it means a different, now this is a different population. This is a population with different characteristics than the earlier one, right? Okay. So it means, right, clearly. So clear, this is clear, right? It means it is less likely that the such a sample came picked from a population which was 70. It means that I am more confident that a sample came from a different population. Now a different population is a new population which is having an average weight of 80. Clear? Hence in that case we reject the null and we say yes, there has been a significant change, something significant change in last 5 years, that now the average weight has increased from 70 to 80. Got it? Is this clear? Right? Okay, next. Of course, when p-value is greater than, we reject, we fail to reject, right? Higher the p-value means higher is the likelihood of the event, right? It means it is more likely that such a sample is picked from an existing population, that I am picking the sample from the same population means that I am more confident that such a sample came from the same population. Hence, we fail to reject the null. Okay, right? So that is all the basics. That is all the summary. That is all the fundamentals about hypothesis. Right now, we discuss some tests, right? Z test, T test. So how do we decide which test we have to use, right? Though we'll be doing it, but this is a, if my population is normally distributed or the population is not normally distributed, okay? Normally distributed data I have or a non normally distributed. Z-test, T-test, and ANOVA are called parametric tests. We'll discuss parametric and non-parametric also in a while. For now, just understand these are called parametric tests. Z-test, we do see Z-test when for a normal distribution, right? When population standard deviation is known or n is greater than 30. Now, n is greater than 30 means I'm taking a sample which is fairly large, right? Sample size is fairly large, right? Okay. So if I pick up large samples, I quickly become closer to normal, right? N means sample size. Yes. Yes, Nutan. N means sample size. Okay. If my sample size is large, I showed it to you at the start of the session. We become closer to normal population very easily, right? Right? So under such circumstances, we use Z-test. T-test, when population standard deviation is unknown or n is less than 30. This is the condition you have to remember. Okay. N is sample size I've mentioned here. Okay. And ANOVA is done when we have to compare multiple data sets. I want to compare. For example, I want to compare the students in school A are smarter than the students in school B. This is my claim, right? If we are comparing large quantity, then n will be equal to 30. Will no. Even if yeah, good question. That really haunts many learners, right? See, even if we have large quantity, right? N Greater than 30. Understand, 30 is a benchmark. Greater than 30, if you are taking samples greater than 30, I am not saying equal to 30 will be small. I am saying sample size is greater than 30. Na? I never said n is equal to 30. Understand? Okay? Is that clear? Lakshmi, right? Greater than 30, can it be 50 also? Na? It can be 50 also. But if I am taking such a big sample, 30 is the benchmark. Na? Understand? Okay, you're talking about T. If you're talking about T test, or you're talking about, you're saying 30 is still a small number, right? When we're dealing with big data sets, right? That is what you're saying, right? I am saying you take sample size even 100 now, but in that case, if you take a sample size 100, then we will do a Z test. I am not saying you have to take sample size 30. It is a benchmark, okay? It could be, suppose I have a bigger population, I might have to collect 1,000 sample size, right? Okay. Okay, then when we have to compare, yeah, it's our choice. Of course, it's not a, it's not as easy as a choice, but of course, many different things. See, if you are collecting 1,000 sample, the cost also, it's not, you are not collecting a sample. I mean, you are not, the sample size is not fixed just randomly. It is fixed keeping in mind various parameters, right? Like cost. So the most important is cost, right? You have to calculate, you have to collect data from 50. Let's say you have to collect the data from 50 samples, and you have to collect the data from 1,000 samples, right? The cost is going to be involved is much bigger. But if you can arrive with 50 samples also, if you can arrive at a result wherein you are 95% confident, will you really want to go for 1,000 sample? Not exactly, right? Right? If you are able to, so it will depend on cost, on how much data can be collected also. I mean, if it is a remote area, it's very difficult to even collect. Let's say you are in a very remote area, um, Himalayas, Ladakh. Population, you will not find 50 people there. I mean, you will not find 1,000 people in kilometers. So is it actually worth looking for 1,000, right? So it depends on various uh, factors, right? Okay, and if the population is not normal, you do non-parametric test. Chi-square is one test we are going to discuss there. Okay, clear? So these, let's, is it clear, these tests, the four types of tests we are going to do? Okay, Z test. Okay, now we are going to start with first type of, okay, first let's understand what is parametric and non-parametric. Yeah, I was thinking I missed out on one topic. Yeah, parametric and non-parametric tests. So before we start with Z test, let's understand this is what are parametric and non-parametric tests, right? So parametric tests are conducted, as I said, when the population is normal, right? It is usually done for data which are, which fall into which is continuous data, right? They are either, they can be measured, either it is a ratio or a interval measurement, right? Is done for them. Okay, and non-parametric test is done for data type which is non-continuous, right? Or ordinal and nominal, right? Categorical data, categorical variables, Okay. Parametric, as I said, we are going to do parametric z-test, t-test, right? And two sample test, we are going to do t-test there. And then we have greater than two samples, we'll do ANOVA. And here we are going to do only chi-square. Rest is not in our curriculum. Okay. Then what are parametric and non-parametric tests? Now this is also a very important thing to, in this entire inferential statistics, right? Non-parametric tests. Okay, first let's see what are parametric tests. Parametric tests like z-test, t-test, they make us assumption about the distribution of the data. They assume that the population is normally distributed, right? They make this assumption that population is normally distributed. Okay, use in the data that is normally distributed. I've already told you this, right? Does not make an assumption about the distribution. They do not, non-parametric test does not make any assumption about the distribution. Okay, hence sometimes they are also called distribution free tests. Hence they are also called distribution free tests. Okay, use in data that are other than normal. Okay, that are not normal or data that is other than normal, we use non-parametric. Okay, now parametric test deals with mean and variance, right? Used to estimate at least one of them, mean or variance. We used to estimate at least one population parameter, mean or standard deviation, from the sample statistics, sample means, right? And this non-parametric deals with medians. Uh, that means variables that which affect the model and which does not affect the model. Lakshmi says that means variables that which affect the model and which does not affect the model. Sorry, I could not get that. Affect the model. You're talking about Lakshmi. You're talking about. Okay. Let's continue. I think maybe you have got this answer. Okay. So non-parametric test deals with. Okay, parametric means. No. Parametric means does not means variable. It means the parametric. Okay, means variables which affect the model. Parameters. Yeah. Right. Parametric means parameter. Yes, parameters. Right. So here, the why do I say parametric here? Because I am trying to estimate population parameters. Trying to estimate. Okay. That is why it's called parametric test. Okay. What are my parameters? Mean and standard deviation. Okay. That is why we call it parameter. Okay. Now, non-parametric test. We do not deal with mean and variance. Can you calculate a mean of a gender? There are 100 females and 100 males. Can I say that average female is some 0.5 and average male is 0.5? Can I say this? No, we are not dealing with averages here. Okay, we deal with medians. Okay, medians. Remember, to calculate the median, what do? We have to sort them, right? Okay, we, or when we are using a small sample size, then also we conduct non-parametric test, or when the data is ranked or ordinal, or is a presence of outliers. Under these four conditions, we use non-parametric test. Clear? Okay. Next. Data is categorical. I've already mentioned data here is continuous. That is why we are able to calculate mean and variance. We cannot calculate mean and variance for categorical data, right? Now, this is a very important point. Information about population is completely known by means of population parameter. That is why, okay, this is clear. Not this one. There's last point which is very important. Yeah, this one. Okay, fine. So information about population is completely known by means of population parameters. Thus, the statistic test is called parametric test. We test the parameters of the population, right? Population parameters. That is why we call it parametric test. No knowledge about the population or its parameters, hence, and still it is required to test the hypothesis of the population. I do not know the population parameters, mean and standard deviation. It's difficult to know the population parameters in real. See, but historically studies have been done, na, right? I am not saying as a company, as a business, uh, you uh, check whether the population is uh, obese or not. But historically, there have been tests done, and there have been characteristics of population, right? That right. So okay, no prior knowledge of the about the population parameters. If I do not have any prior knowledge of the population, I cannot test mean and standard deviation, no? So in the such circumstances, I use non-parametric test. Okay, H0 is made on parameters of the population distribution. We know H0 is free from population parameters in this. We'll see this, right? It is free from population parameters. When we do chi-square, we'll see this, right? Okay, now this point is important. Parametric tests are powerful. Now understand this point very well, and if you don't get it, you can ask me, right? This is an important point. Parametric tests are powerful. These tests are powerful as parameters or statistics are calculated from original data, and they include these tests include the impact and magnitude of the data. Means mean and standard deviation. Remember, mean and standard deviation is calculated by picking or taking the value from each and every data point. Yes. So population mean and population standard deviation would have included data from each and some data, right? Some it has extracted some value from each and every data point, right? That is why they are powerful. Now, can you tell me in median? I remember this example. Is median calculating a median? Does it include information from each and every data point? Just no, right? Median is just the middle point. So if you remember, I'll show it to you also. I'll quickly take two samples, data set 1, data set 2. This is 1, 1, 5, 100, 5, 6, and 7. Median is 5. 1, 1, 5, 100, and 1000. Median is again 5, right? So median is not taking data from each and every sample, is not using information from each and every sample rather. Okay, is this clear? Point clear? Right? So that is what I'm saying. But if I take an average of these two, my average is going to come very different. Exactly. It is so parametric are powerful because they are extracting information from each and every value. But when I talk in terms of means, non-parametric tests are not that powerful. They, there is a loss of information when we calculate ranks or means. The impact of the magnitude of the data is lost. I am not calculating any magnitude if I calculate mean or if I calculate median. Am I calculating any magnitude? No. Magnitude means the extent, the extreme, right? Clear? This point is clear to all of you? Exactly. It's just a position. That is why I mentioned rank, right? Ranks. Okay. Quickly, now I've already told you Z test, T test, F test is a NOVA only, and chi-square. These are the 4 tests we are going to do. Starting with, okay, this is we have already done data types. Okay, so I'll just skip degrees of freedom. What is degrees of freedom? Before we start with the test, degrees of freedom. Okay, so the degrees of freedom. And anyone knows what is degrees of freedom? Okay, so let's see what is degrees of freedom. Related to sample selections, right? It is related to sample only. See, degrees of freedom in statistic indicates the number of independent values of, that can vary in an analysis without breaking the constant. These are the number of values that are free to vary in the data set. Means, I'll explain this, right? Here's an example. It is an estimate of the number of independent pieces of information that went into calculating the estimate. It is not quite same as the number of items in the sample. Degrees of freedom, usually people confuse it with the sample size. It's not the sample size. It is the number of independent items that can, independent pieces of information that can go into the model or go into the calculation, right? So let's see this. Suppose I ask you, I'll take an example. A, B, C, D, E, right? Suppose I say the total of these 5 values, 5 samples that I collect, right? Sorry, the total of these 5 numbers is 100. So, can I put any value to A? Yes. I am free to take value in A? Yes or no? Right? Put some random value. Why? Why can't I put any value? Even put a negative, because then it will be balanced. Because I am saying total of these 5 numbers is 100. I can put any value. Okay, Rohit. Exact. Yes, Nisha. That is what I am saying. Right? I can put any value. I can put any. I am free to put any. I am free to put any value for observations. 20, 45. I am randomly putting. Okay. Now I calculated this. Can I? Am I free to put the fifth value now? When the total is 100, can I freely put the fifth value now? No. I have to now, even though it is a negative value now. See, E has become negative now, right? So what will be E? 100 minus sum of all these 4. Even though it is a negative value, but I am now, my E value is fixed. I mean, it cannot be freely put the way I freely put these 4 values. Okay. So degrees of freedom. This is called degrees of freedom. So if I have 5 numbers, my degrees of freedom is going to be 4. I can put freely any values to 4 of the observations, but then once I put 4, put values, put free values. Sorry, once I put any values to 4 of the observation, fifth cannot be the free one. Okay, so that is why degrees of freedom is usually n minus 1, right? N minus 1. Okay, that is number of observation minus 1. Clear? Okay, quickly now moving to Z test. Okay, so Z test. First, to understand what is a Z test, we'll understand what is standard normal distribution. Forget this word standard, you know normal distribution? Yes? You know, all of you know normal distribution, right? So, how much is the percentage of the observations within plus minus 1 standard deviation? 68, right? Then you have 97 and then 99, right? Roughly, right? 68 something. Yeah, yeah. I'm not saying give me the exact somewhere. I think 68. Yeah, yeah. 68.2, 95, and then 99. Okay, right? Okay. Now, what is standard normal distribution? It is also known as SND, right? It is a normal distribution, and this is called Z distribution. Standard normal distribution is called Z distribution. It's a unique normal distribution where mean is equal to 0 and standard deviation is equal to 1. Okay, if my it's a normal distribution which is, so all the normal distributions, all the different types of normal distributions can be, remember scaling we had done when we were doing heat maps, we did scaling, right? So all the normal distributions, there can be different types of normal distributions, we'll see in the next slide. All the different types of normal distribution, right, can be standardized into, can be converted or rescaling. You do the rescaling and they can be converted into a standard normal distribution where mean is equal to, where mean will be equal to 0 and standard deviation will be equal to 1. For a SND, area under the curve will always be 1. So we rescale the normal distribution and we convert it into a standard normal distribution. Area under the standard normal distribution is always 1, right? You can calculate the area by calculus also, those who know calculus, right? But it will be 1. Okay. Normal distribution can be standardized by converting its value into z-scores, right? So can be standardized by converting its value into z-scores. So when you standardize the values of a normal distribution, these are called z-scores. So if this was my mean, if in a normal distribution, let's say this was my mean, and the mean was let's say 100, some value 100, right? So this 100 will be converted, will be equal to or will be same as 0 in the standard normal distribution because the mean 100 is converted or rescaled into 0, right? So how can you rescale 100 to 0? By deducting 100, right? Yeah, exactly. That is what I'm saying. So values, in reality you have values, in reality you have values here like 100, let's say, if I talk in terms of weight, 80, 60, 100 weights, but we, when we convert them, we call them z scores, right? When we convert them, when we rescale them, those are called z scores. Okay, clear? This point is clear? Z score tells you how many standard deviation from the mean each value lies. Of course, z score will tell you how many standard deviation. So z score are going to go 1, 2, 3, 1, 2, 3. So z score tells you how many standard deviation the mean, from the mean each value lies. So plus 1 minus 1 is of course 1 standard deviation, right? So z score of plus 1 and minus 1 is plus and minus 1 standard deviation, right? Standard deviation is nothing but a value only, right? And this holds 68% of the data. Okay, so standard normal distribution is a probability distribution. The area under the curve between 2 points. Now this is also the area under the curve under 2 points tells you the probability of a variable taking the range of values. Of course, right? If I ask you what is the probability that my, let's say my average weight of a male in a city is 70, right? So this is my mean. I say what is the probability that if I pick a random male, his 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 weight will be between 60 and 50, right? So it will be this probability if this is 60 and this is 50, right? It will be this probability. That is what it is saying. The area under the curve between 2 points tells you the probability of the variable taking that range of values. The total area under the curve is 100% or 1. Clear? Now, how do you convert a normal distribution into a standard normal distribution? See, notice all of these are normal distributions. Can you see? Notice some might be peaked, might have more skewness, more kurtosis. Some might have less kurtosis. Some might be on the right side, some might be on the left side. But this blue one is a standard normal distribution. Clear? This blue one is a standard normal distribution. Okay? I can convert all of them into standard normal distribution. This is A, blue color, A is standard normal distribution. This red color, B. Notice now when I say B, I'm talking about this one, red color. Okay. In B, what is the mean? Mean is 0, isn't it? Mean is 0 and standard deviation is 0.5. See, if standard deviation is half that of blue, right? Okay. Because it is squeezed, right? Because it is squeezed. So standard deviation is less than 1, right? Then C, which is this purple one, notice mean is 0 in purple one, but standard deviation is double, right? Stretched because standard deviation is greater than 1. D, which is this green one, notice mean is 1. Now this is the mean, right? This is the mean 1, but and standard deviation is also 1. It is shifted towards right, right? This one is also normal with a mean of 1 and standard deviation of 1. It is shifted on the right side. And similarly, mean of -1 is this one, orange. Mean of -1 and standard deviation of 1 shifted on the left because mean is less than 0. All these different types of normal distribution can be rescaled and converted into a standard normal distribution, which is blue color. Clear? We can rescale it using this formula, right, of rescaling. I think this is a formula wherein, but you don't have to do it anyways, right? So now benefits of standard normal distribution. Data points are referred to as X in the normal distribution. X means the actual variable I am studying, right, or the actual variable of interest. They are called Z scores in Z distribution, right? These variables are converted or transformed into Z scores. When we convert the entire distribution into a standard normal distribution, they are called Z scores. A Z score is a standard score that tells you how many standard deviations away from the mean an individual value lies. We have seen this. Benefits of Z distribution. Now, once I convert two different normal distributions into a standard normal distribution, won't it facilitate comparison? It has been standardized, so can I compare the two distributions? Yes? Right? So, benefits of the Z distribution, it compares Z score on different distribution with different means and standard deviation. So, comparison is possible. Normalized scores for statistical decision making. So, it has normalized the scores, which becomes the standard measurements, right? So, it normalizes the scores. Find the probability of observation in a distribution falling above or below a given value. So, because the area under the curve is 1, I can find the probability also of the event happening. Find the probability of the sample means significantly different from the known population. So basically, I can calculate the probabilities also of an event occurring, of an event not occurring. All this can be calculated. Okay. Okay. Z test. Now coming to Z test. Statistical test to determine if two population means are different from the variance are known, means are different when the variance are known and the sample size is large. So I've already told you, when do we do Z test? When sample size is large, okay, and the population variance are known, variance or standard deviation both, right? Mean and standard deviation are known. Then we conduct a Z test. Used to test hypothesis in which the Z test follows the normal distribution. Also, T test assumes the standard deviation is unknown, where Z test assume it is known, right? So this is when we come to T test, then we'll get to know this, right? So T test assume, in fact, sorry, I've already discussed this, right? Uh, this one. T test is done when standard deviation is not known. Population standard deviation is not known. Okay. Okay. This is a normal distribution, standard normal distribution, right? Okay. When do we use? When we use Z-test, samples are drawn at random. Samples are taken from independent population. Population variance is known and sample size is greater than 30. Okay. In Z-test, population parameters are known. Correct. Newton, right. Assumptions. There are some assumptions. Quickly, I'll run through this. Scale of measurement is continuous. I have already discussed. Most of this I would have discussed. Data collected is representative and randomly selected. So, of course, whenever you collect a sample, it has to be representative and random. Data when plotted on a reasonable results in a normal distribution. Data when plotted is reasonably large. It results in normal distribution and homogeneity of variance. Homogeneous or equal variance exists when the standard deviation of samples are approximately equal. So homogeneity of variance is another assumption. Okay. Now this is a formula for calculating Z statistic, but we don't have to do this formula at all, right? R is going to do this for us. So we will now move to, I think what we'll do is we'll start with Z test tomorrow, right? We'll start in R. We'll do Z test tomorrow, but let's take an example of Z test, right? Let's take an example of Z test. Understand this example of Z test, and then tomorrow we will do Z test in R. Okay, and then thereafter we'll continue with T test. Tomorrow we are going to do T test. Then we will do ANOVA, and we'll also do chi-square. Okay, tomorrow we will do all these tests, and after we do all these tests, we will start with sampling. What are the different techniques of sampling? This is this one. Different types of sampling, right? We'll do this tomorrow, and then we will, in R, we will learn what are, how do we start with modelings? What things we do when we do modeling? Okay. First thing we do is we split the data set into test and train, right? So splitting the data set into testing and training data set, right? So test and training data set. Okay. Okay. So quickly we'll end up today's session with this example of Z test. Okay. A principal at a certain school claims that students in his school are above average intelligence. Okay. A random sample of 30 students IQ score was taken and the mean was 109. Okay. Is there a sufficient evidence to prove the principal's claim? The mean population IQ is 100 with a standard deviation of 15. Now see, the mean population is 100. So if I have, first thing I have to prove, what claim I have to test? Tell me what claim I have to test. So what is H1 I'm saying? Exactly. Greater than 100 is the H1, right? No, no, no. Population mean H1 is greater than 100, right? What we have to test? He is saying principal's claim is above average intelligence. And what is the average intelligence? 100. IQ score is equal to 100 is the average score of the population, right? So he is saying they are more than average. So my claim that is going to be tested is greater than 100. H1 is greater than 100, right? So what will be the null? Less than equal to 100, right? I have written equal to, it should be less than equal to. Okay, right? So null and hypothesis, null and alternate clear. Alpha, as I said, significance level. I am ready to take up 5% risk. I am ready to accept 5% error. So by you can assume it when nothing is given. Just assume alpha to be 5%. Okay. Now, how do we do this z test? We create this. We created this normal curve, right? And as I said, mean is 100 here, right? 100 is the mean, and 109 is what I have to test, right? A random sample. Sorry. Uh, yeah. No, I think there was one more thing. If a person came up with, is there a sufficient evidence to support principal's claim? Mean population is 100 and standard deviation is. So if a person who comes up and random sample is collected and yeah, 109 is what we have to test, right? 109. We have to test 109, right? I missed it. So 109 we have to test whether this represents the entire population or this is actually the score or not, right? Or this is actually the population mean or not. So what we have to test whether what he's saying that his students are having a mean IQ of 109, right? That is what we have to test. Okay. So what we do is, this is the formula, though you don't have to do it. If you look at this, where I mention the formula for z test is x bar minus mu. Mu is 100, x bar is my observation, right? 109 is my sample mean and 100 is my population mean, right? 109 minus 100 upon 15, which is the standard deviation, divided by under root of n. N is 30, right? I divided by square root of n. So this comes out to be 3.2, right? So now here you have to manually, when we used to do, we will go to z tables and see what is the population, what is the z score from this, right? What is the z score for, what is the area under the curve? This becomes the z score. This is the z score, right? X bar minus mu upon standard deviation upon under root n. This becomes the z score. Now add this z score. We used to look at the table. Now we don't. You don't have to do it, right? The value is 3.28. So we used to look at z score. And how do you look at the table? You first look vertically. Look at 3 point. Okay, we got this 3 point, right? Then 3.28, right? So 3.2 is here. So if you notice it, this is my 3.2, right? So let me highlight it. This is my 3.2 column or row, and 8. 8 I think is this one, right? So this 995 is my area under the curve. Now this, from this table we get area under the curve on the left side, right? This table gives you area under the curve on the left side of 109. Okay, is this clear? This table gives you this area. So what is the area on the right side then? If 999.999 for 0.995 is the area on the left side, area on the right side will be 1 minus 0.999, right? So which is 0.0005, right? Now this area I compare, this is the area I compare with 0.5, 5%. Which one is less? Of course this is less, right? So when p value, this is the p value, right? When p value is less than 5%, what do we do? When p is less than 5 significance level, alpha, we reject the null, right? So final decision is we reject the claim of his, that the, we reject the null, sorry. We reject the null and we accept the claim of the principal, right? That yes, what he's saying, if he's saying if we have picked up a sample of 30% and average score is 109, it means yes, his claim is correct, that the students of his school are above average intelligence. Is that clear? This example is clear? Exactly, right, Nisha, right? Right, there is another example. I would want you to go through that example on your own, right? So we'll take a pause here. Hopefully you have what got a good ground and basics of hypothesis and inferential statistics, right? We will be using it when we to reject and accept the independent variables in the models, especially in regression, logistic, right? We'll be using this concept wherein based on the p-values, we are going to reject the variables that we really will include in the model or we exclude in the model, right? That is why hypothesis, as it said, inferential statistics is the basics, is the foundation of data science also, right? In modeling especially, right? Okay, great. Thank you so much, everyone. Yeah, yeah, of course. Don't worry. I will be sharing all. In fact, I've already shared it, Shubham. I've already shared it. Here you, not this one, this one. See, it's there. Oh, sorry, I did not share the screen. It's already shared, right, Shubham? Okay, then we'll continue tomorrow. And thank you so much, everyone. Appreciate that. Keep practicing, and I'm sure you will be able to get a good grip on data science. Okay, you will have a very good foundation on data science once you are done. RStudio pages, RStudio I've already, is there. RStudio is also there. See, there are some RStudio files. They are also there, right? If you see the folder, they are also there. Okay, great. Then see you tomorrow. Goodbye.
Thanks for a wonderful session, sir. Hope you guys enjoyed today's session. I have provided the feedback link in the chat box. Please do provide your valuable feedback for today's session. And if you have any other generic related queries, you can put it in the chat box.
Julie, it's there in the Google Drive. Let me share the link of the Google Drive then. There you go. Okay. Okay. Goodbye.
Guys, please do provide your feedback by using the link which I have shared. Okay, guys, thank you all. We'll meet in the next session. Thank you so much. We'll end up the session for today. ನಾನೇನು ಹೇಳ್ತಾರದು ಏನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಇಲ್ಲಿ